Hello and welcome. And this presentation is a decision-focused analytics briefing for MKRC 7042. The audience is the module leader and teaching team, and the central question is simple. Which support interventions should be prioritized to improve student performance and satisfaction? The presentation uses a cleaned 10x Unit 3 style survey dataset. The raw file contains 1,616 records, and the clean analysis file contains 1,600 responses after duplicate removal and validation. I will walk through the dataset, the cleaning process, the core findings, the resulting decision package, and a critical review of the analysis using CRISP DM and Hicks-Peng style quality principles. The first and most crucial correction in this project redesign is the framing. Getting this right from the start is essential because it defines the entire scope and direction of the analysis that follows. The original task was not to produce a polished, generic presentation that simply reports data. That approach often lacks actionable insight. Instead, the revised task is to show real analysis that leads to a specific, evidence-based decision. This is about moving from data to a defensible recommendation. So the problem is framed managerially from the perspective of the end user. Which support interventions should the teaching team prioritize to improve student outcomes? To structure the work and ensure a rigorous process, I use the cross-industry standard process for data mining, or CRISP DM. The business understanding phase translates the managerial problem into a data problem and defines the decision for the teaching team. Next, the data understanding phase examines the survey structure, the variables available, and the initial respondent profile to assess its quality. The data preparation phase is the technical work of transforming the data, where I clean the raw file into an analysis-ready file. The analysis phase then applies statistical techniques to this clean data, using exploratory charts, grouped means, and correlations to uncover patterns. Finally, the evaluation phase interprets these patterns, translating the analytical findings into a practical and targeted support package for students. To ensure the analysis stays focused on the managerial problem, it is guided by 4 key questions. First, who is in the dataset? We need to understand our student sample. Second, what factors are associated with performance? This helps identify key drivers of success. Third, what factors reduce satisfaction? Pinpointing these issues is critical for improvement. And fourth, which support intervention do students actually prefer? This ensures our solution is student-centric. The raw survey file contained 1,616 records. The cleaned analysis file contains 1,600 responses across 25 variables. The difference is explained by the removal of 16 duplicate response IDs. The cleaning workflow also standardized inconsistent labels across program type, employment status and region, corrected small numbers of out-of-range values, and filled minor numeric gaps using simple imputation. This matters because the earlier version of the presentation was criticized for not demonstrating real use of data. Here the logic is auditable: raw file, cleaning checks, cleaned file, and then analysis. The charts that follow are not decorative. They are built from the cleaned dataset and tied directly to the decision question. Before interpreting performance and satisfaction, we need to understand who is in the data. The sample is not an abstract group of students. A large share is balancing study with substantial work pressure. In the cleaned dataset, 58.3% of respondents are full-time employed. 32.6% report no prior analytics experience, and 47.0% identify time management as their main challenge. That profile matters because it changes the interpretation of the findings. The core issue is not laziness or lack of interest. It is the interaction between workload, confidence, preparedness, and practical support. Any recommendation that ignores those constraints will be poorly targeted. The first major finding is that assessment preparedness is strongly associated with performance. Mean self-reported performance rises from 51.6% among students at preparedness level 1 to 85.0% among students at preparedness level 5. The correlation is 0.684, which is a strong positive association. The managerial interpretation is direct. Students do not only need more content, they need a stronger sense of readiness before assessment submission. This points toward early diagnostic checks, clearer assessment scaffolding, worked examples, and targeted readiness support before students reach the submission deadline. The second major finding is that data anxiety is strongly negatively associated with performance. Mean performance falls from 89.0% at anxiety level 1 to 58.1% at anxiety level 5. The correlation is minus 0.707, which indicates a strong negative association. That should change how we think about support. Data anxiety is not just a soft emotional issue, it becomes an operational performance issue. If students feel intimidated by data tools, code, charts, or analysis workflows, their outcomes are likely to suffer. This supports practical clinics, tool walkthroughs, low-stakes practice exercises, and confidence-building support. The third finding links time pressure to satisfaction and support preference. Mean module satisfaction falls from 9.69 out of 10 at time pressure level 1 to 5.06 out of 10 at level 5. The correlation is minus 0.560, showing a meaningful negative association. The support preference data points in the same direction. 68.4% of respondents choose recorded walkthroughs as the most useful support intervention. That is not a small preference. It is a dominant signal. For a sample with many full-time employed students, replayable asynchronous support is not a nice extra. It is the support format most aligned with their constraints. The decision package follows directly from the findings. First, introduce early assessment preparedness scaffolding. That means readiness checklists, worked examples, marking criteria walkthroughs, and short diagnostic checkpoints before the final submission window. Second, reduce data anxiety through practical clinics. Students need short, applied sessions showing how to clean data, build charts, interpret correlations, and translate findings into recommendations. The point is not to overwhelm them with theory, it is to make the workflow visible and repeatable. Third, design support around time pressure. Since many respondents are employed and recorded walkthroughs are the strongest preference, the support model should be asynchronous first. Live sessions can remain useful, but replayable walkthroughs should become the backbone. A strong presentation should not pretend the analysis is perfect. In fact, acknowledging the limitations and potential weaknesses is a sign of intellectual honesty and builds trust with your audience. It shows you've thought deeply about your work. To structure this self-critique, we follow a Hicks-Peng style logic, a robust framework for evaluating data analysis. This involves 5 key principles: matching, exhaustiveness, skepticism, transparency, and reproducibility. First, matching. The data must directly match the decision question at hand. Are we measuring what we claim to be measuring? In this case, the survey is useful because it directly measures preparedness, along with related factors like anxiety, time pressure, satisfaction, performance, and support preferences. These align well with our core questions. Second, exhaustiveness. The analysis considers a broad range of factors, including user profile, behavior, outcomes, and preferences, but it does not capture everything that might affect performance, such as prior experience or external life stresses. Third, skepticism. It's crucial to remember that these are associations, not causal proof. We've found connections, but we haven't proven that one thing causes another. For example, we should not claim that reducing anxiety automatically causes higher performance without further, more rigorous testing like a controlled experiment. Fourth, transparency and reproducibility. The workflow clearly documents all raw to clean data processing steps, the variables used in each chart, and the summary statistics. This comprehensive documentation makes the entire analysis auditable, allowing others to scrutinize and verify our work. Finally, we must state the main limitation clearly. The 10x dataset is simulated. It's a realistic model, but it's not real-world data. Therefore, the safest and most logical next step is to repeat this same workflow on the genuine Unit 3 survey or another verified real dataset to validate these initial findings. To conclude, our comprehensive analysis identifies 3 dominant levers that significantly influence student outcomes: assessment preparedness, data anxiety, and time pressure. These are the critical factors we must address. First, preparedness is strongly associated with higher performance. Students who feel ready for their assessments consistently achieve better results. Conversely, data anxiety is strongly associated with lower performance, creating a significant barrier to success for many. And finally, time pressure not only reduces overall satisfaction with the learning experience, but also directly increases the need for more flexible support options. Based on this evidence, the recommended decision is therefore clear and targeted. We must prioritize assessment preparedness scaffolding to build student confidence and capability from the outset. This should be complemented by practical data confidence clinics to directly combat anxiety and on-demand recorded walkthroughs to alleviate time pressure. That package is aligned with the student profile and directly traceable to the findings, ensuring we provide evidence-led, not generic, support. The risk note attached to this analysis is equally important and must be carefully considered. It's crucial to remember that this 10x dataset is simulated. While this means the architecture is analytically stronger than the previous submission, the model's conclusions are based on generated, not observed data. Therefore, a formal resubmission would be safest for full validation. This is especially true if the same workflow is applied to the genuine Unit 3 survey or another verified real dataset in the future. The immediate next step is therefore to validate these powerful findings using real survey data. Once confirmed, we can then finalize this targeted support package for implementation and begin making a real difference for our students.